Hey everybody, back for Unit 4. We're looking at Newton's laws of motion. So forces, dynamics. So we're going to look at Newton's 3 different laws of motions, first, second, and third. Look at weight, normal force, making sure that we can solve problems using free body diagrams, and also looking at friction, forces on inclines, and then a general problem-solving approach that's helpful. So hopefully by now we know that force, we're looking at a push or a pull, and this is what is either needed to get an object moving or to stop an object from moving. So anytime you want to change the velocity, you need a force, which means changing velocity is acceleration. So we touched upon that when I talked about the centripetal acceleration in Unit 3. And magnitude of the force is going to be the size of the force. You can measure that on a spring scale, bathroom scale, which is a type of spring scale. With Newton's first law, it's the law of inertia. We know that an object at rest wants to stay at rest, and an object in motion wants to stay in motion, and in that straight line path. So if there's no net force acting on something, it's going to keep moving or remaining still, whichever is its motion at the time. So we do have what we call inertial frames of reference, and this is a frame of reference in which Newton's first law is valid. So that's not a rotating or accelerating frame of reference. The AP exam doesn't really get into this, so I'm not going to go any further with it. Just so that we make sure that we understand, you have mass and you also have weight. Mass is the amount of inertia in an object. It's measured in kilograms. It's the tendency of something to stay in motion or to stay at rest. It does not change based on location. It's always the same. It's based on the amount of matter an object has. This is different than weight. Weight is a force. Mass is not a force. Okay, so that's really important that we know the difference. Okay, Newton's first law, again, object in motion tends to stay in motion, object at rest tends to stay in rest. So that means that you need a force in order to change the motion of an object. And so the question becomes, okay, how does then the change of the motion and the force relate? And we can find this by doing experiments. And we find that the acceleration of an object and the force applied to it are directly proportional. And we also find that when we look at the acceleration of an object, the acceleration on an object and the force on an object, the acceleration and the mass are inversely proportional when you relate them between force, if you have a constant force. So ultimately that leads us to Newton's second law, that the net force on an object is equal to its mass times acceleration. So that means if you've got a force that you're acting on a really large, massive object, it's going to produce a small acceleration. If you take that same force on a small, less massive object, it's going to produce a much larger acceleration. Hence, why things like semi-trucks and trains need such greater stopping distances than a little Mini Cooper, right? The Mini Cooper, not a lot of weight compared to those, and so you apply the brakes and short stopping distance. You apply that force on a semi, it's going to take a lot longer to stop because the acceleration is so much smaller. So that's why you don't want to tailgate the Mini Cooper. Same thing with motorcycles. Don't tailgate me when I'm riding my motorcycle because I can stop on a dime and you might not be able to. Okay, so ultimately F is your net force in Newton's second law. M is the mass of the object in kilograms. Acceleration is measured in meters per second squared, and so you get some of the forces, or F net equals MA, and we measure force in newtons, which is a kilogram times a meter per second squared. Okay, now when you have Newton's second law, force is a vector, and so you need to take that into account, just like we did with projectile motion and velocity. We kept the x and the y separate. You're going to want to do that with forces as well. Keep the x and the y separate and combine at the last minute using trigonometry. Okay, stating Newton's second law again. And here are some different units. We're going to stick with the SI system. We're going to use kilograms for mass. We're going to use newtons for force. Just so that you're aware though, pounds is a unit of force. It's not mass. So that can get confusing for people, because if you ask someone in Europe how much they weigh, they'll tell you how many kilograms, and that's not actually their weight, that's their mass. Okay, Newton's third law says that when you have a force acting upon an object, the object will exert a force equal and opposite on what's acting. So when you hit your hand on a desk, the desk hits your hand back. So, you know, if you were to crash your car or something and hit a tree, well, no, really, the tree hit you is what you can tell mom and dad. This is what allows, like, ice skaters to get moving, is when they push on the wall pushes back on them, and since there's a very low amount of friction down below, they can slide across the ice. This gets confusing for people when you play tug of war. Okay, so if you have, I'm looking to see if I got a little piece of string I can demonstrate this with. Yeah, wire will work. If you have your two teams pulling on a rope for tug of war, this team over here can only pull as hard as this team here. You might have some really strong people over here and some really weak people. This team still cannot pull any harder than this team. Okay? The way you win tug of war is who can get the biggest normal force pushing into the floor to get the greatest amount of friction to actually do the moving. Okay? But the actual within the rope, this only as great as that pull. Okay? Rockets can propel through Newton's third law. So the gases, they get pushed out of the rocket by the rocket pushes the gases, and the gases push back on the rocket, and the rocket moves. Okay, this is how you walk. You have to actually push against the ground pushes back on you. Swimming, right? You're pushing the water behind you, the water pushes you, and you go forward. This is always a crazy diagram to look at. So if there was no ground whatsoever, okay, and the assistant pulls on the sled in his nice red tights, the sled would pull back on the assistant, nobody would move. But because they're also in contact with the ground, and the friction between the sled and the ground is different than the friction between the assistant and the ground, you can get an actual overall net force of the system moving forward. Weight is gravity accelerating a mass. Okay, so your acceleration is gravity, mass is mass, and therefore the resulting force is your weight. Okay, normal forces are the reaction force from a surface, and they act perpendicular to the surface. So when your surface is flat, your normal force is straight up. But when you incline your surface, your normal force then goes at an angle, but it's still 90 degrees to the surface itself. Okay? Now, normal force does not just equal weight. It all depends on the situation. So our first diagram A here, yes, the normal force is equal and opposite weight. But for B, you've got the weight plus the additional force of someone pushing down, so the normal force has to counteract both the weight and that push. In situation C, someone's pulling up a little bit, so the normal force doesn't have to support as much as the weight, so you see that it decreases. Okay? Now, if this is just a really simple Newton's second law program, or problem, you're pulling up with 100 newtons against a weight that's 98 newtons, so we have a net force. What's the acceleration? Okay? And so here you can just plug in, and you know your net force is 2 newtons, and your mass is 10 kilograms. So to find the acceleration, 2 newtons divided by 10 kilograms. And so 0.2 meters per second squared is going to be your acceleration. Okay? When you have Newton's second law problems, when you have force problems, always draw a free body diagram. Okay? Now, here, our free body diagrams are showing the components in them, Do not put the components in the free body diagrams on the AP exam. You will lose points, okay? But always you want to draw a free body diagram. You want to show the force. You want to label the force. If you can, draw it to scale for the magnitude, okay? Break things into components and resolve the components, the x and the y. Apply Newton's second law to the x direction, apply it to the y direction, and then use that to solve, okay? Tension is a force that exists within like a cord or a rope or a wire, okay? And it will transfer force from the hand to the box, okay? You've got a bunch of different examples here with the angles. So when we look at pulling at the 30-degree angle, we've got only the x component of the force is going to go into moving the box in the horizontal direction. The y component of the force is going to make the normal force less. Okay? Oh, everybody loves elevator problems, right? So you can do these a couple different ways, and I believe I posted an example earlier in first semester if you want to go back and look. So what you can do is if you have your two equations like they've set up here for the elevator, you can subtract them from each other, or you can add the equations depending upon what's going on. What I like to do is say I know the acceleration of the system is going to be the same, and so I solve for A and then set the two equations equal to each other, and it works out similarly. So basically I just have the one equation because I know I just set the acceleration for the entire system. Okay. We don't really get into advantages, so we don't need to worry about that here. Okay. Again, components of forces. I'm going to let you just look at those examples. Now, this is really interesting here. If we look at the tension forces, they are different in the different ropes. Okay. In the top rope, that rope has to support the weight of both bucket 1 and bucket 2, whereas the bottom rope only has to support the weight of bucket 2. So when the system accelerates, that bottom rope has less tension in it than the top rope. Okay? And so you want to treat each rope separately. Okay, so ultimately the question would be, okay, wait a minute, how is she going to move if she's pulling and it pulls back oppositely and all that? Well, we can figure that out using Newton's third law. Okay? Friction happens because of microscopic roughness that happens on the surface, and so those little things dig in, those little ridges dig in, and they impede motion. Friction is always going to act opposite the direction of motion. Two types, static and kinetic. Static, you're not moving yet. Kinetic, you're moving. Static friction will build up and peak right before you can get an object moving. So if you've got an object and you're pulling on it, but you've just started pulling it, the static friction will be equal and opposite whatever you're pulling, and it'll pull until it reaches its maximum, okay, which is the maximum coefficient of static friction for two given surfaces, and then if you pull at that force, you'll get the object moving and the frictional force will drop because kinetic friction is going to be less than the maximum static friction. And often I'm asked, well, how do we determine the coefficient of frictions? You do it experimentally, okay? And you do need to know the normal force to know the frictional force because they are perpendicular to each other, but the normal force is part of our equation for finding the frictional force. And it's right here. The force of friction is going to equal the coefficient of friction times the normal force. This one shows kinetic sliding friction. We know there's rolling friction. We know there's static friction now. Okay? All right. So again, static friction builds up, builds until you overcome it, and then you move into kinetic friction. your force of kinetic friction is always going to be less than your force of static friction. And there's some of our experimentally found coefficients of friction. Okay? And a graph showing exactly what I've been describing. Okay? We've got some different examples here. In example A, because the man is pushing down on the child to push him, he's actually increasing the normal force that's provided by the ground, so the force of friction is going to increase. Whereas B, he's pulling upward, and so that decreases his normal force, so the force of friction will decrease in a corresponding manner. Okay. Same with the block. You've got your tension forces are going to be equal and opposite over a massless frictionless pulley. Once you start dealing with pulleys where we have to take into the moment of inertia and things like that, the tension can be different, varying one rope to the next. But here we're going to ignore it, and so we can find our tension force using all of our different equations. For inclines, okay, your normal force is going to be perpendicular to the surface. Friction's going to be parallel to the surface. So you take those into account. Your gravity force is what you want to break into components. And we've done this quite a bit. Okay, so some problem solving approaches. Read the problem carefully, read it again, draw a sketch with a free body diagram, choose a convenient coordinate system. So for the incline, take that coordinate system, tilt it, list the known and unknown quantities, find the relationships between them. You'll be able to pick Newton's second law almost always, estimate the answer, solve algebraically. So with the estimation, does this seem reasonable? Keep track of your dimensions, double check. Okay? All right, here's an angled problem. And so you notice that when you break your gravity into components, you've got similar triangles. So the angle between the y component of gravity and gravity itself is the same as the angle of the incline. And that's really useful. And so